Hello, Geography and Tourism Studies 3P22 students. This is Jeff Boggs, and this is Lecture 9 on ANOVA, and it focuses on the swimming pool example from Rogerson, so from your textbook. You'll notice that down here I say the slides accompany Lecture 9 notes in R code. I am posting the notes that these slides are based on and R code that works through this example plus follows along with the notes. And in the notes there are citations for any images that you'll happen upon. Okay. So one-way analysis of variance is used to compare three or more means. It assumes that your data are normally distributed. So not only the population data, but also if your sample size is less than 30, that each of your samples are roughly normally distributed, and it assumes something called homoscedasticity or equal variance. So this means that your samples have variances that are roughly all the same size. To help you remember some of the key points we're going to talk about today, we're going to just briefly go over means and variances. So remember that the arithmetic mean, or what we're calling the mean in this course, is the average. So what you in normal English would call an average. And it is a measure of central tendency. That is the middle or center of the distribution of our data set. The variance is the standard deviation squared. So you're more familiar with standard deviation, but you've seen variance as well. And so standard deviation, when you square it, that gives us the variance. Both of these, so both variance and standard deviation, are measures of dispersion. So that means that they measure the amount of variability or spread in the distribution of our data set, right? So today we're focusing on ANOVA, so it's useful to talk about the logic of ANOVA. So it's used to run hypothesis tests on something called using an F distribution, and we calculate something called an F statistic and compare that to the F distribution, which we'll cover later on in this lecture. But basically what ANOVA does is that it compares both where the middles of our distributions are and how spread they are. So the middle of each sample, and it uses this then when it's calculating how much dispersion or spread there is within each group as well as between each group. So if we take k random samples, so k is the number of groups that we have. So in our example today, we have 3 groups, so k is equal to 3. So if we take these random samples from the same population, and especially if these random samples are of similar size and are large enough, we would expect that these k sample means would usually be good approximations of the population mean. So we're saying that if we have 3 samples of, say, in this particular instance, we have size 8, which is a little small, but we'll go with that. And if these 3 samples of size 8 all came from the same underlying population, then we would expect that their sample means would be relatively close to each other most of the time. And we could make use of confidence intervals to talk about how precise we are about that. So we're not going to go into that right now. So what this means is that we expect the centers of samples, so we expect the sample means to be relatively close to the center of the population that they're taken from. So we would expect our sample means to be relatively close to the population mean of the sample that they're all taken from. And so if all samples were taken from the same population, we would expect all of these samples to both produce sample means that are pretty close to each other, but also pretty close to the population mean, right? And this, of course, is assuming random samples. Beyond talking about centers or sample means, we also, oh wait, before we do that, this all might sound familiar, and it should, because it's sort of at the heart of the logic of Z and t-test for two sample means. So, but in those cases, we just have two samples. And as a further aside, you might recall from reading your textbook that you can actually run an f-test on two sample means, and it will give you the same results as a t-test. But normally we use a t-test for that. So, okay. So in terms of the logic of ANOVA with regards to dispersion or to the spread, it's kind of a similar idea to what we saw with the center or with sample means. So this logic holds for sample variances and also sample standard deviations and other measures of dispersion, so that we would expect that if we took three samples, that not only would there three, and if these three samples all came from the same population, we would expect not only their sample means to be similar, but their variances or their standard deviations to be similar as well. And so more generally, then, we expect the dispersions of samples, so sample variances or sample standard deviations, to be close to the dispersions of the population. So hold on a second. Sorry, there was a small child in a grocery delivery. Okay, so we expect the dispersions of samples so we expect sample standard deviations and sample variances to be pretty good estimates of population variances and population standard deviations, right? So that's sort of the underlying logic here. In the next slide, I'll try to show an example using box plots. Okay, so if we think about box plots as both a way to measure the center and the dispersion of a sample, and bear in mind that, remember, the middle of a box plot is the median, not the mean, but it still will work for what we're going to do. And if we use traditional box plots, so not Tukey's box plots, so we're going to use traditional box plots where the whiskers are the minimum and maximum values, we can consider a situation in which first we've got three samples of about the same size, and this is the first one's box plot. That looks awful. There. We've got this box plot. We'll say that that's where the median is. We've got this box plot. Median is there. There are its whiskers, and then we have maybe this as our third one. So these are three box plots that could conceivably represent three different samples that were all drawn from the same population. So their middles are relatively close, and their dispersions, or their variances, so range, if you will, are actually all about the same as well, right? And so when we go back to this notion of homoscedasticity, one of the assumptions for ANOVA to work, where we have variances that are about equal in size, this would be an example of a case where we probably can assume that there's homoscedasticity, so that these three samples all have about the same kind of dispersion, though with ANOVA we measure that using the variance, and their middles are all kind of somewhere in the same area as well, right? And that these are taken from a random sample. So this is a case in which our null hypothesis of no difference, which is often written, if I remember correctly, for ANOVA, it's like it's supposed to be mu1 equals mu2 equals, these are supposed to be Greek letters, mu3. So this would be a case in which we fail to reject the null, right? So this is consistent with them all having been drawn from the same population. Okay, on this side over here, if we use kind of box plots to illustrate this concept, here's a case, I'm going to draw us a case in which we have three samples that are less likely to have all come from the same population. So these are terrible looking box plots, but I was not able to get my Wacom pen to work with this. So there's our third box plot, right? And so here's a case where we're pretty sure that, like, certainly for this observation down here, this one looks a lot different from these other two. So for this sample, its mean is probably a lot different. Well, it would have to be fairly different from these other two. I mean, this also depends upon what our scale is over here, but let's assume that that's a substantial difference. Okay. Whereas these two might be from the same population, though they're this one looks a bit lopsided, the second one here. Okay. And what these three have, though, in common is that their variances could be somewhat similar, right? We could also have another case where, so in this one, in the second case here, the means are different. We could also have a case where our dispersions are like very different, right? So maybe this one extends all the way down there. So this bottom quartile is really stretched out, right? And so this third case here is one that probably would violate our assumption of homoscedasticity from the get-go. Whereas the second case here is one that's more suitable for a standard one-way ANOVA, right? It's because our dispersions are probably all pretty close to each other, whereas in this third case, this third group over here, its dispersion is really lopsided, plus it may not be very normal. So, okay, so that might help you think about the kind of the logic in ANOVA, so that it looks to see if, on the one hand, let's go over here, your three best estimates, so your sample means, are our best estimates of our population means, that basically it's saying that they're all kind of similar to each other, right? So, whereas our alternate hypothesis, and then sort of a corollary with this, is that also the variances are the population variances would all be equal to. Okay, so in this one, for our alternate hypothesis, the only one you ever have with ANOVA, thank God, is that, or at least with One-Way ANOVA, is that the three sample means, sorry, the three population means are not equal. So that's what this one is. And both of these formulations occur later in the notes in these slides. So they'll be written a bit more clearly. Okay, let's progress to an actual example. Okay, so in Rogerson, he has some data that seems to have been collected by asking people in a central city, in suburbs around it, and in rural areas beyond that, how many days did you swim last summer? So we have in each of these columns, for each of these samples, the number of days that people swam in each of those locations, of these 8 randomly selected people. Okay, so we have 3 groups. So we have central city, there's group 1. We have suburbs, that's group 2. And we have rural areas, that's group 3. And then for central city, suburbs, and rural, we each have 8 observations, right? So we've got 1, 2, 3, 4, 5, 6, 7, 8, right? Okay. So all together, we've got 24 observations when we pool, P-O-O-L, when we pool these 3 groups together, that gives us 24 observations. So here we have calculated, and Rogerson does this for us in chapter 6, we have the first sample mean. So the sample mean for the central city is 48.63 days. For the suburbs, it's 63.63 days. And for rural areas, it's 67.63 days. And so our null hypothesis is going to be that basically these 3 means are essentially equal to each other. So did everybody swim about the same amount in each of the 3 kinds of locations, right? And then he's also calculated standard deviation for us. So for central city, it's 19.88 days. For suburbs, it's 12.66 days. And for rural areas, it's 11.43 days. If you square these, that gives us the variance, right? So and we'll write this over here to make that clear. So that equals our variance. Oh gosh, I write like a 5-year-old with this thing. Okay. So we've got our mean, our standard deviation for each of these samples. In his textbook, Rogerson will draw these, or the formula will be like an X with a little plus sign next to it, right? Looks more like a T. Whereas in the way I learned it was you draw X with a single bar over it for these. And then for this would be our first standard deviation, or standard deviation for the first group, standard deviation for the second group, and standard deviation for the third group, right? So this then would be mean of X for the first group. It's got a little 1 next to it. The mean of X for the second group, have a little 2 next to it. And the mean of X for the third group, we'll have a little 3 next to it. So down here, we have a grand mean, which is what you get when you take these 24 observations up here and find the mean for those, right? So you take all 24 of these, add them up, divide them by 24, and that gives us 59.96. So you take these 24 observations, so there's 8, 16, 24, take those, add them together, divide them by 24, it gives us 59.96 as our grand mean. He writes that in his notation as x with a plus and another plus sign by it. So, whereas I always learn this as just x with a bar with the double bar, so x with 2 bars over it. Okay, his grand standard deviation, it then is just the standard deviation of these 24 observations. And he writes that simply as just S. So, because it's a sample standard deviation, right? Or sorry, yes. And so, actually up here, that S squared, our variance, would actually be S squared with a little K next to it for each group. Because there's K groups, there's 3 groups, so there'd be S squared 1, S squared with a 2, S squared with a 3, right? And so, and then this one, S squared by itself is going to be, oh Christ, that's the wrong one. Hold on. Oops. This is his notation for the grand standard deviation. Okay. And in earlier weeks, we learned how to calculate all this stuff. So, okay, so let's move on to the first step. So the first step is that we want to, if we're going to do this manually, we want to calculate what's called the total sum of squares. So this is the total variance in for among all the observations and all the means, right? And in fact, this right here is telling us that, so this xij, this means, so this first summation over here, that deals with our 3 groups. So we use group 1, then group 2, and then group 3. And then these j's over here, they tell us that for, so N1 would be for group 1, N2, so if you replace that I with a 2, would be group 2, and N3 would be, you replace that I with a 3, that would correspond to our 3 groups. So all this stuff here, all these double summations are just telling us that we, as we perform these operations, so this xij, this basically the first, so x1, 1 would be the first observation from the first group, so that's whatever the first observation is for the central city, and then x1, 2 would be the second observation for the central city, all the way, and you go through all 24 observations, and you subtract each of those observations from this grand mean. So you take your first observation, you subtract it from your grand mean, and then you square that. And then you take your second observation, you subtract from that the grand mean, you square that. You take your third observation, subtract from that your grand mean, and you square that. And so you do that 24 times, and that gives you a number that's equal to your total sum of squares. So your total variance, right? An easier way to do that is to use this formula over here, or at least easier for the example I'm working through today, because I don't want to have to do this 24 times, is that in this case, n is the total number of observations because there's no subscript, right? So that's 24 minus 1 times, remember s squared with no subscript? That's just the that's the grand standard deviation, if you will. So that's the standard deviation associated with all 24 of the observations. So let's solve for this. But before we solve for this over here, let me back up and just briefly show you this. So TSS, so the total sum of squares, is equal to what's called the between sum of squares. So that's the sum of squares of the difference between each sample mean from the grand mean, plus the within sum of squares, which is the sum of squares. Those are supposed to be s's. So the within sum of squares is the difference between each sample mean and its observation. Or sorry, each sample mean and each of its observations, if I remember correctly. And we shall see those here in a little bit. The next slide covers BSS, and the slide after that, WSS. So the fact that TSS can be, the fancy term is decomposed or broken into a BSS and a WSS, this allows us to check our work for doing this manually, right? So BSS and WSS should always add up to be TSS or awfully close to it. There might be slight rounding errors, but that's a different issue, right? Okay, so let us go and solve for this over here. So we have 24 total observations. So 24 minus 1 times our variance, right? Which is our standard deviation squared. And in this case, our standard deviation is 16.69. So 16.69. That's terrible. So part of the reason it's taken me so long to prepare these slides is that I've been experimenting with different ways to write out numbers, and this is the best I've come up with. So, all right. Okay, so 24 minus 1 times the quantity of 16.69 squared. So this here is this over here, and that is the variance of our grand variance, if you will. It's the variance associated with our grand mean. And so this becomes 23 times, this becomes 278.5561. I'm going to just round it to 56. And if you do this in a computer, you can then round at the very end. So, but to save space, I'm doing it this way. So then I multiply 23 times 270 times, hold on. Actually, let's go back and use the full number it gave me. So 278.5561, right? I'm not going to round it here. I square that. So that times itself gives us, oh, sorry, we've already squared that. So 278.5561 times 23 gives us, this gives us 6,406.7903, which is, there's the approximate sign right there. It's kind of a squiggle like that. Looks like a tilde. So gives us, if we round it a wee bit, 6,406.79, right? So what this means is that when we add up our BSS and our WSS, they should equal this number or something awfully close to it, right? So that's why we want to know that. So it's our total sum of squares, right? Or the squared residuals. Okay, step 2. Calculate the BSS, which is the between sum of squares. And so this, what it's doing is it's saying that we sum up, so that we perform this operation for each of our groups. So Nj, so that would be N1, N2, and N3. That's going to be the number of observations in each group. And this here, this x bar j, or the mean of j, so the sample mean of j, is just the sample mean of group 1, and then we'll use group 2, and then we'll use group 3. And then we'll subtract each sample mean in turn from the grand mean over here. So we take each sample mean, we subtract it from the grand mean, and then we square that. So we do the first sample mean, subtract it from the grand mean, square that, take the second sample mean, subtract it from the grand mean, square that, and then do that again for the third mean. And then each time after we've squared those, we multiply each of those times the number of observations that were in that group's sample. Okay, so let's work through an example. So Central City, we've got 8 observations, right? We have 8 observations times our first sample mean. So the sample mean for the Central City was 48.63. Right? We square that. And let's finish this one first. So 48.63 squared gives us 2,364. So it'll be 8 times 2,364. 0.8769. So it's supposed to be a 6 there. Yep. And 8 times that number gives us oh, wait, nope, that's wrong. This is where teaching in person is so much easier, because by this point, somebody in class would say, hey there, Jeff, you left something out, I think. And you know what I left out? Look here. I left out, so I included this, but not the grand mean. Thought that looked funny. Okay, here we go. Let's go back. There's our grand mean. It's going to be, and this is the number we'll reuse a couple of times. It is 59.96. So 59.96. 0.96 squared, right? So we subtract this from that, or this from that, and we square it. So 48.63 minus 59.96 gives us negative 11.33. So that's going to give us 8 times negative 11.33. Oh my God. 33 squared is then going to give us 11.33 times itself gives us 128.3689. So 8 times 128.3689 equals so times 8, that should equal 1026.9512. So it's going to be 1026.9512. I'm just going to leave it at that right now. Right, so that is for Central City. So that's the between group variance that's due to how the Central City mean differs from the grand mean. Okay. Let's try this. Okay, so then there's suburbs. Okay, and so for the suburbs, we're going to have 8. No, let me just save some room here. So we're going to have 8 times our sample mean for the suburbs at 63.63. Minus 59.96 squared, and that's going to equal, so that will equal 3.67. So these two numbers are really close to each other, so we shouldn't be surprised that they're quite small, that difference is quite small. So we've got 8 times, what did I say, 3.67? Yep, 3.67. But first we have to square 3.67. So 3.67 times itself. This comes out to be 13.4689. So, wait, got ahead of myself. So we have 13, so we have 8 first, times 13.4689. Right? Okay, and so 8 times 13.4689, so 13.4689 times 8, it gives us 107.7512. Right? And I'm going to underline these in dark blue, just to help us remember that's from the suburbs, right? And so up here, we know this. Use purple, I guess, for central city. So there's the central city, right? For the suburbs, we had 107.752, and then we repeat this again for rural areas. So let me see if I can do rural, W-R-U-R-A-L. So 8 times, and in this case, our sample mean for rural was 67.83. Minus 59.96 alone. Squared. So that gives us then 8 times, so 67.83 minus 59.96 gives us 7.87. Oh my goodness. Squared. And then 7.87 times itself should give us 61.9369. So 8 times 61.9369. So that should give us 495. 495.4952. Right, and I'll underline that with like a dark green there. Okay, right, so the last thing that we have to do is we have to add all of this stuff up. So these three, this, and this. So 495.4952 plus 107.7512 plus 1026.9512 equals, oh, sorry, hold on. This number should be 0.63. Let me fix that. So that should be a 6.3, and then everything that's changed I'll rewrite in black. So that means the difference is 7.67. So let me make that there's to show that it's changed, and then 7.67 squared is 58.8289. So it is 58.8289. So there's 5, there's 8, and then 8, 2, 8, 9, which then changes this to be 470. So 8 times 58 point, that's supposed to be a point. Make that a big circle there, right? So 8 times 58.8289 gives us 470. 0.6312. There. All right. And then we add these three together, and that gives us the total BSS, the total sum between sum of squares. Okay? So 470.6312 plus 107.7512 plus 1026.9512 gives us, this gives us 1,000, do this in red again down here, so 1,605, no, fiddlesticks, it's supposed to be 5,605, .3336, right? Which I'm going to be lazy. I'm going to round that to approximately 1,605.33, or you could do 0.334. Okay, so this is the BSS we've just calculated, and now we will move on to the within sum of squares calculation. Okay. So the first thing you'll notice is that the within sums of squares calculation, or the formula, there's two ways to do it. So in that way, it's a bit like the total sum of squares, which had two different sets of solutions, two alternate ways to come up with the same number. So the first part here, all of this, what this is telling us is that for each group, we take the observation and then subtract it from that group mean. So we take the first central city observation, subtract it from the mean of the central city. We take the second central city observation, subtract it from the mean of the central city, and we would do that all together 8 times, right? Because there's 8 observations. And then we would square that, and then we would repeat that for suburbs. So we take the first suburban example, or the first suburban observation, and subtract from that the suburban mean, square that difference. Then we would take this for the second suburban observation, subtract that from the suburban mean, square that, and keep doing that, and we would repeat that then for the rural examples. Okay, so we also have this way over here, which is a little less cumbersome if we've already calculated the standard deviation for each of the groups, which Rogerson has been kind enough to do for us. And what this tells us is that, so NJ, so that's the number of observations in group J. I wonder if that should be a K. Anyway, so this number is going to be 8. So for our first group, we've got 8 observations. For our second group, we've got 8 observations. For our third group, we've got 8 observations. And then J, so J is going to correspond to our group. I wonder if the notation through here switched. Anyway, so we'll have 8 minus 1 times the variance for the first group, and then 8 minus 1 times the variance for the second group, and 8 minus 1 times the variance for the third group. And the reason that this is 8 is because in each of our 3 groups, we always have 8 observations. If you had 7 observations in your first group and 12 in the second, then this n would change, right? So in our example, we have the same number of observations in each group. So to calculate this, we first, we're going to calculate it, basically, we do 3 operations. So we do it for each, do it first for the central city. I'm just going to put CC. And so for the central city, it's 8 minus 1 times the variance for the central city. And so he didn't give us the variance for the central city. Instead, he gave us the standard deviation, which for the central city was 19.88. Right? Oh, Jesus. Okay, let's fix that. There we go. Okay, so that's going to give us 7 times 19.88 squared, which is going to be, if we square 19.88, should give us 395.2144. So 395.214. Yeah, fiddlesticks, 4. Right? Oh, and all of that times 7. Hold on. Right? So, and then 7 times 395.2144. It gives us 2,766.5008. Right? So that's for Central City. And next we're going to do suburbs. I'll just call it the burbs. And for the burbs, we have 8 observations. And our standard deviation for the suburbs was 12.66. We square that. So that's going to be 7. And this time, I'm going to do, well, fiddlesticks, all of this right here, 12.66 squared. I'm just going to put it in there to save us a bit of time, or space at least. So 12.66 times 12.66, it should give us about 160.2756. Which should give us, so 7 times 160.2756 should give us 1,121.9292. So 1, actually let's put it over here, 1,121.9292. And then, so we've got Central City, we've got the suburbs, and then we have rural. Let's see if I can write that all there. Rural. Okay, so 8 minus 1. And our standard deviation for the rural was 11.43, it looks like. 11.43 squared. So 7 times, let's go ahead and, oh, Jesus. square 11.43. So we get 130.6449. Then we multiply that times 7, which gives us 914.5143. I'll write that over here. 914.5143, right? And the last thing that we do, because we have this summation symbol up here, is that we sum these three values, and that gives us our WSS. So we add together 914.5143, 1121.9292, and 2766.5008, and that gives us 4,802.9443. 443, right? So that's the contribution of the within sum of squares deviation. Okay, so then what we can do is we can take WSS and BSS, and if we add those together, hold on a second, it won't let me go back. One moment. So if we add this number, so I'm going to use blue, we're just going to check our work, 4,802 plus 9,443 plus, can't remember exactly what number I wrote down on the previous slide. Software doesn't let you go back. So, but it was close to 1,605.33 something. Those together, so this is our WSS, right? And this is our BSS. Together, they should add up to our TSS. And this is a way that before computers were readily available, like you lucky lot have, this was the way we would check our work. So 1605 plus our 0.33 plus 4,802.9943 gives us 6,408.2743, which should be pretty close to 6,406.79. So that's pretty close to 6,406.79. So those differences are probably due to rounding errors somewhere, or where I rounded early. And also, I'm not actually sure what we had for our TSS. It was close to this, but it might have been slightly different. I can't go back and actually look because this software will have a conniption if I try to go back. Okay, so this, though, suggests that we're on the right track. Our numbers are really close to each other. Okay, and that those differences are likely due to rounding and or me having written down on paper a number that's slightly different from the TSS that we actually calculated. So, yeah. All right. So, let's go to the next slide. Okay, so now we are at a stage after we've calculated our BSS, this thing, and our WSS, we are at a stage now where we can actually calculate an F statistic. So this is sort of like a T or a Z statistic. So we compare this to this value that we get, this F statistic, from our observed values, compare that to some cutoff value in the sort of old-fashioned way of doing, of conducting hypothesis tests. So alternately, software will look up the p-value associated with your F statistic. So, all right, so we've just taken about 30 minutes to calculate the BSS and the WSS. So the BSS, if I remember correctly, was something like 1,605 point, I'm just going to use 33 divided by k minus 1. So k is the number of groups that we have. So 3 minus 1. And then all of that, actually, let's go back here. Make this look more like a 6. Oh my God. All of this is then divided by our WSS, which is also divided by the total number of observations minus the total number of groups. So our WSS was around, if memory serves correctly, about 4,802.94-ish, if I remember correctly. And then all of that is divided by n minus k. So n, in this instance, is, and this is where Rogerson kind of jumped ship with his notation, that is supposed to be the total number of observations when you pool them. So P-O-O-L, and you put them all in the same group. So that's 24 minus 3, right? Okay, so let's then go here. So this simplifies to 2, that simplifies to 21. So 1,605.33 divided by 2, all over. And so basically we do all of this stuff first on the top, and then we can do all this stuff on the bottom. Actually, I think there's ways that you can sort of cross multiply and it'll work as well. Let's not go down that route. Okay. So that's a division sign right there. Let's make that more like a division sign. There. And then down here we have, make that equals there, equals, so 4,802.94 divided by 21. Okay, so 1,605.33 divided by 2 should give us 802.665, while 4,802.94 divided by 21 should give us 228.71, and a lot of numbers after that. I'm just going to round that to 228.711, which then equals, so 802.665 divided by 228.711 gives us gives us 3.509 blah blah blah, continues on. I'm just going to round that to 3.51, which actually is the same thing they've gotten in the textbook. That's good, right? So this is our F statistic for our observations. And so what we now do is we need to compare this to our diagram to see if we reject or fail to reject our null hypothesis. So remember, this is sort of like a t-score or a z-score when we do when we conduct a t-test or a z-test, right? So there, we want to compare 3.51 to our rejection area. Okay, so this lovely image here shows a F test or an F distribution table. So, or F stands for Fishers. So he's a statistician who has lots of things named after him, and including this table. So what's weird about ANOVA is that you have two sets of degrees of freedom. So you have degrees of freedom of the numerator. So that's the stuff on the top. And for us, that was 2. Hold on a second. Okay. So we've got, we remember how we divided the, was it the BSS by 2? Yeah, we divided the between sum of squares by 2. For that, we've got 2 degrees of freedom. And then, because that's the numerator, for the denominator, for the WSS, we had 21 degrees of freedom. Because for that, you take the total number of observations minus the total number of groups. And so we're there, right? So if we use this table like so, we basically cross-index these 2 points, and this is a Fisher's table for 5%, or alpha equals 0.05, which is pretty common actually for this. So alpha, there's my little fish looking thing. So alpha 0.05, right? And so it tells us that 3.47 is where is our critical cutoff value. So our rejection area begins everything, it starts at 3.47 and continues on to positive infinity, right? So we want to recall that number, 3.47. I'm writing it down on a sheet of paper so I don't forget. Okay, so we might call this our F crit or F critical. Often when people write these out, they will have like F so 0.05 to tell you that it's for alpha equals 0.5 and then a comma. And in this case, it would be 2. That tells us that we had 2 degrees of freedom on the numerator. And then a comma 21 to tell us we had 21 degrees of freedom in the denominator. And then, and all of this stuff over here would actually be in subscript. And then that for that, 3.47 is our critical value. Sometimes they'll put a little star there next to it also. Okay, so this, when we found this, that was pretty quick, wasn't it, compared to what we previously done? Okay, so now let's draw our little diagram. Okay, so in the notes, you'll see that, like the T distribution, the F distribution is dynamic, but it's even more dynamic because it has 2 sets of degrees of freedom instead of 1. So that means that drawing it is a big pain in your backside. What I tend to do is just assume, for the sake of argument, it generally looks kind of like, oh, that's a terrible looking line, that it generally looks like a chi-squared distribution. So I'm going to, I got to use some different colors here, don't I? So I'm going to draw it kind of like this, and we haven't covered chi-squared distributions. So, but it looks sort of like this. This value over here is 0, and then over here is going to be like positive infinity, way over there, right? So the nice thing about these is that they're only ever one-tailed tests, or at least the way that your book is showing them. So there. Okay, and so what we need to do is, let me see, let's try that. So we want to figure out, so we'll use that as like the rejection zone. So if our value, that's a J right there, falls to the right of this point, and that point is actually going to be 3.47. That's our F critical, right? I can even put like a little F crit there. And this scale is measured in terms of F, and this is like the frequency, basically, or percentage of the area under the curve. A way to think of that is like that. And so remember that, like all these blasted hypothesis tests, when we draw these, the area under the curve sums up to 1, and these things trail off, in this case, to positive infinity, right? So this is a bit janky looking, so bear with me. It's not very smooth. So these are supposed to be smoother lines. Okay, so if we get a value that's greater than 3.47, that means we reject the null hypothesis, right? So anything from here on over. And let me just drag that up a bit more. If we get anything that falls over here, so between basically 0 and 3.47, so an F value of 0 to 3.47, you'd get an F value of 0 if your basically your numerator and your denominator were both the same value, right? And would you get that? That'd give you a 1, actually. Yeah, I have to think, so forget that. So a 1 would be where your numerator and your denominator, so your BSS and your WSS, are the same sizes. So okay, let's go back here. Okay, so if we're over here, we fail to reject, which older books would just say means you accept your null hypothesis. But in any case, what that means is that there's no statistically significant difference between your different samples. Okay, so we calculated 3.51 Let me do this. So if we end up over here, right? Those are terrible looking lines. If we end up somewhere over here, this means that we reject the null hypothesis. And lo and behold, our actual F value is 3.51, right? So 3.51 falls into the zone of rejection. And let me just flesh this out a bit. So this 3.47 is our F critical, right? So because 3.51 falls over here in the area where we reject the null hypothesis, we reject our null hypothesis, which means that these, so therefore, oh wait. We reject the null hypothesis of no difference, and are wrong one time in 20, right? Because remember our alpha level is 0.5. So we reject the null hypothesis of no difference is what this means. So what you follow this with then, hold on, are, if you want to know more, is you use Tukey's HSD if you've rejected the null hypothesis in a one-way ANOVA and you want to figure out which observations are responsible. And I will make a little video about that, at least for R here in the next day or so, which observations are responsible. Okay, so what I want you to do is look at the notes. In the notes, it will also include lots of empty space for you to sort of work through those problems that I showed here. So you kind of develop an intuition. And then my next video is going to be a bit on the R code for this. All right. Thank you for sitting through this hour and 20 minutes of what I'm sure was scintillating blah, blah, blah.